All right, so d dx of the derivative with respect to x of the natural log of 5 to the power of cotangent of 3x. There's a lot of ofs in there, right? Every time you say of, you have a chain rule. So does anything need to be rewritten? No, not really. But you might want to put parentheses around the 3x. If anything, all the other layers are pretty intuitive. So here we go. When we take the derivative, the d dx goes away. So we learned yesterday that the derivative of the natural log of x is 1 over x. So we haven't really gone over the chain rule part of it, but you know that the chain rule is always in the house, right? Like a ghost that won't go away. But a benevolent ghost, right? So the natural log of blob's derivative is 1 over the blob. 1 over the blob. Okay, and that takes care of the natural log part. And then times the derivative of the next layer. So you go inside, it's the natural log of 5 to the power of. So that's the exponential layer. It's going to be itself, cotangent of 3x. I'll keep it in there, times the natural log of 5. That's part of the exponential rule. Don't forget that because it's not base e. Times, now we go into the exponent and it's cotangent. So its derivative is negative, good, cosecant squared of 3x. And that's why I put parentheses because I don't want dot negative. And then times the derivative of the innermost blob, derivative of 3x is 3. And that is your answer, unsimplified. Now, if we're going to simplify it, does anything good happen? Yeah. Those divide out, don't they? Yeah. And we're left with a constant multiple that is -3 natural log of 5. And then times the cosecant squared of 3x, which we don't even need parentheses anymore. So I did simplify, but you didn't have to. That's what it simplifies down to. Now, one last little thing here. I doubt this is going to be the case, but what else could we do? Well, you got natural logs. So simplify early and often, comma, especially when you have logs. If I just brought the -1 factor up from the -3, if I just brought the -1 factor up, that would be the natural log of 5 to the -1st. 5 to the -1st is also known as 1/5. So that would be another equivalent final answer. But that one's kind of gross because now we have a fraction. So what might end up happening is if we did have the natural log of 1/5, we might write it as natural log of 5 to the -1st and bring the negative out front to make it look like above. What if we left the negative out front but brought up the 3? Then it would be negative natural log of 5 to the 3rd. 5 to the 3rd. 5 times 5 is 25. 25 times 5 is 125. So the natural log of 125 times cosecant squared of 3x. Okay. So that would be another equivalent version. But I doubt either one of those would actually be the right version. In fact, both of those, if that was the answer, would look probably like the one we got, because the whole purpose of logs is to make things smaller, to bring things down. But just exploring with logs. So you should learn to play with logs at the end of every answer that ends up having a log in it. Just kind of it'll keep you agile, keep you nimble, prepared for answer choices, and it's kind of fun, right? I play with logs a lot growing up, but most of the time they were Lincoln logs. But then by the time I was in 3rd grade, I switched to natural logs. Yeah. Okay. Comments or questions on the warm up? Everybody warm? Okay. Good. All right. Let's move on to then example 7. Now that we know the derivative, absolute value function. What the heck are we going to do with that? Well, if we look at this function, f of x equals the natural log of the absolute value of x. I want to do a couple things here. First of all, when you compare it with the one we just did, let's call it g of x equals 1 over or natural log of x. Is there a difference in those two functions? In other words, what does there's the absolute value. What does the absolute value do to our inputs? Anything? It makes all the inputs positive before they get to the natural log. Yeah. So if you look at g of x, we said yesterday, the domain of a log function is going to be everything that is strictly greater than 0. Right. Can't take the log of a negative number. But on the left-hand side, if we're nuking the inputs before we take the natural log of them, are negatives now allowed? Yes. Okay. So the domain of this function f is actually the set of all x, such that we still can't take the domain of or the natural log of 0, and the absolute value of 0 is 0. But we're allowing negatives into to play now, right? We're including more values. Yay, more inclusive. Okay. Now let's think of what the graph. It says to verify the graph. Let's think of what the graph would look like. Okay. So I'll draw your y-axis, your x-axis. Let me go ahead and color code this. Let's say that g of x is going to be in red. Okay. So we know the graph of the natural log of x looks like this. It has a vertical asymptote at 0. And of course, it passes through the point 1, 0. And it increases at a decreasing rate. It's concave down, we say. So the points would be like e comma 1, e squared comma 2, so on and so forth. We talked, I hope, maybe. I'll do this one in the green that it's in for Christmas. We talked in honors pre-cal last year about the absolute value transformation. And maybe you talked about it, Ms. Skurhoff. Okay, if you're taking the absolute value of the input, what that transformation does is, as you can see, it graphs all x's as if they were positive. So positive x and negative x are going to have the exact same output, right? What type of symmetry does such a function have? Y-axis symmetry. Yeah. By definition, this one is going to be an even function. Okay, with y-axis symmetry. It has to be. If positive and negative x's graph is the same. So what you can do then to generate the graph is this. If x is already positive, the absolute value of a positive number is still the positive number. It's still going to look the same on this side. So you can trace over that branch right there. But what's it going to look like in negative land? Well, if you want to try out a few points, let's just try the natural log of the absolute value of -1. So right here at -1, well, that's going to be the natural log of 1. And of course, that's 0. So -1 and +1 have the same value, right? -2 and 2 are going to have the same value. Of course, it's going to have y-axis symmetry. So all you have to do to create this graph is let's just kind of come down here with the rule of thumb. We're going to keep positive x's alone. And that's going to be quadrants 1 and 4. Okay. Then, and this is the big one because it has y-axis symmetry, then we're going to reflect these values, or just these, across the y-axis. Now, for the natural log function, there was nothing there to begin with. But if you did have another function that had y values already to the left of the y-axis, they would be gone. You wouldn't even see them. Because by definition, when you take the absolute value of the input, positives and negatives all graph the same, and they graph as if they were positive. Okay, so the question is now, what would be an equation that would allow us to find the derivative of the natural log of the absolute value of x? Well, to do that, we're going to break it down into a piecewise function, okay? Kind of based upon this graph that we just generated. If x happens to be strictly greater than 0, you can kind of read these piecewise functions like that. If x is greater than 0, then we kind of read from right to left. Then we're going to let it be just plain old natural log of x, right? And I traced over that over here in quadrants 1 and 4. But, okay, else, I guess you could say, if x is less than 0, what am I going to do? I'm going to sketch the natural log of the negative x, because in any function, if you multiply x by a negative, that's a y-axis reflection, right? So that gives you this half here. In other words, I'm going to manually make it positive. You can think about it that way as well. If you have a negative number and you're trying to take the absolute value of it, you got to manually make it positive by multiplying it by a -1. Now, of course, it's not even defined at 0. It's just greater than 0 and less than 0 because it's still not defined at 0. All right, now I can find the derivative. Let's find the piecewise derivative. So f prime of x is going to be, well, we'll just take the top piece. What's the derivative of the top piece, natural log of x? 1 over x. So it's going to be 1 over x when x is greater than 0. And now by the chain rule, the derivative of the natural log of -x. Well, that's the natural log of blob. So its derivative is 1 over the blob. And then times the chain rule, the derivative of the blob. What's the derivative of -x with respect to x? -1. Yep. And that's going to be when x is less than 0. So if we simplify that now, we get it's going to be 1 over x when x is greater than 0. And a negative divided by a negative is positive. It's going to be 1 over x when x is less than 0. Hey, what do you notice about the two pieces now? They're the same. So do I really need to split it up into a piecewise function if it's the same piece? No. That's like taking a regular Snickers bar and cutting it in half and saying, now I have 2 Snickers bars. No, it's the same Snickers bar, right? So I could just say that f prime of x is actually just 1 over x. And you know what? I wouldn't even have to say what intervals to use. I wouldn't even have to say don't use 0 because it's still not allowed in the equation. So notice what we just did there. We just, through a piecewise function, said this: the derivative with respect to x of the natural log of the absolute value of x is just what? 1 over x. Was that any different from the regular derivative, the derivative of regular natural log of x? No, it was exactly the same. Exactly the same. The only difference is the domains. That's it, right? You always start with the domain that you're given. So for this one, x has to be greater than 0. Even though 1 over x on the right will allow you to use more, we don't see that because the natural log of x doesn't give them. And over here, we include all the negative counterparts. X can't be 0. So this is one of the very, very, very few times where you'll hear me say, if there's an absolute value there, it doesn't matter. It just goes away. When you take the derivative of the natural log of the absolute value of x or the absolute value of blob, it's just 1 over blob. It goes away. Okay, it's like the only time that it doesn't really matter on the derivative. Just realize we're expanding the domain. Well, let's see if that holds true then for the graph, right? Let's go ahead and do this now one more time. Let's go ahead and graph natural log of x right here. And let's sketch its derivative. We'll call this y equals the natural log of x. And then let's choose the derivative to be purple. The purple is 1 over x, right? 1 over x looks like this. So is the purple graph the derivative of the green graph? Yeah, well, it is, right? But remember, 1 over x also lives down here. It has 2 different branches. But for regular natural log of x, we don't even see that, right? So let's go through this process again. If I analyze the slopes of the green graph and plot the slopes at the same value of x where I'm tangent, it should be the purple graph. So let's give ourselves a little curve surfer here. I've tried this before with somewhat success. Okay, there's my tangent line. If I then, right there, my slope is a very big positive number, right? It's a steep line, so it's a really big positive number. Look at the purple graph at that point, at that x value. It's way up there coming from the vertical asymptote. That's good. As I go to the right, notice my slopes are still positive, but now they're not as steep. So my y values of the derivative are still positive, but getting smaller. As I continue to go further over here, this is not working. Over here, my slopes are still positive, but now really small. And because the natural log of x goes to infinity, slowly, the tangent lines are approaching a horizontal tangent line, right? So they're approaching zero. So the slopes go from a positive huge number to a positive number approaching zero. They'll never equal zero because there's not a horizontal asymptote, but they'll approach zero. And that's exactly what's happening with the purple graph. The y values of the purple graph are the slopes. We go from a big positive, slowly decreasing, approaching zero. Now, we don't get to use this purple branch on the derivative in quadrant 3. But if I look at the natural log of the absolute value of x, okay, there's that piece. And by the same analysis, we're still able to use it. But if I draw the other piece over here, now it works. Watch. This red piece is negative all the way through. So our derivatives are entirely negative. They're coming from something that's flat, which is near zero, to something magnitudes-wise that's going to infinity in the negative direction. So there you go. You can graphically see now that the derivative of the natural log of the absolute value x is still 1 over x. We just get to use both branches. Ho, ho, ho. It's all about what? Perspective. Yes. Yes. Boys throw stones at frogs in fun, but the frogs do not die in fun. They die in earnest. Yeah. Okay. Who's Ernest? Right? And why is he eating frogs? Okay. Have a fantastic lunch. Yes, ma'am.